Okay, so today will be the last content, okay, for CS 2010. Okay, so we'll be talking about one last problem called shortest, all-pair shortest path, okay, or what I call the 4-line wonder algorithm, okay. So after this quite short lecture, I think about 45 minutes, then you'll take a break, and then we'll proceed with your written quiz too, okay. Yeah. Okay, let's start. It's an outline. We'll very quickly review your single source shortest path, and then we'll introduce the all-pair shortest path problem, okay, with one motivating example, okay, and we'll show the algorithm for solving this all-pair shortest path problem, which is Floyd-Warshaws. Okay, so I'll just show you the short code and the basic idea, but I will not discuss the DP formulation. It's actually a DP solution. Okay, so the DP formulation, if you want to discuss it, is quite deep, so I won't discuss it here. Okay, but after that, I'll show you a few very cool Floyd-Warshaw variants. Okay, so you can use Floyd-Warshaw to solve many different problems, okay, other than this all-pair shortest path problem. Okay, review question. What is single source shortest path problem about? Number one, finding the shortest path between a pair of vertices in the graph. Source to destination. Finding the shortest path between any pair of vertices. Finding the shortest path between one vertex to the other vertices in the graph. Number one. Number two. Number three. I don't see many hands. Are you sure you're ready for quiz 2 afterwards? Okay. Okay lah, it's number 3 lah. I hope everybody knows ah. So if you don't know at this point, it's a bit worrying. Yeah, okay. Okay, so let me introduce this new problem, all-pair shortest path. It's not a new problem, okay, it's just a variation of your single source shortest path. Okay, so a motivating problem. Let's talk about all-pair shortest path using this problem. Okay, it's called computing the diameter of a graph. Okay, what's the diameter of a graph? It's basically defined as the greatest shortest path distance between any pair of vertices. Okay, so you find the shortest path between any pair of vertex, the greatest shortest path you can find. That is the diameter, okay, of your graph. So why do you want to calculate the diameter? One example would be, for example, if I want to know what is the maximum or minimum, the maximum number of clicks I need to get from one web page to another on the internet. So you can represent web pages as nodes, right? And clicks as the edges linking one web page to the other, right? So what's the maximum number of clicks? It's basically the diameter of this graph. Okay, so that's one very simple application. Okay, so if I give you this very simple graph here, okay, so only 1, 2, 3, 4, 5 vertices, okay, undirected, okay, unweighted graph. So what is the diameter of this graph? How do you find out? So I have to look at the shortest path between every pair of vertices here, right? Correct? So let's see. Between 0 and 1, what's the shortest path, of course? Only 1, right? One edge, one, correct? 0, 2, also 1, right? 0, 3, also 1, right? 0, 4, also 1, right? After that, 1, 2, 1, 2, also 1, right? 1, 3, 2, right? 2 edges, yeah? So shortest path cost is 2. 1, 4, 1, 4, is it 3? 1, 2, 3, 4. Is it 3? No, it's 1, 0, 4, right? It's still 2, okay? Then 2, 3. 2, 3 is just 1, right? 3, 4. 3, 4 is just 1. So the biggest shortest path you can find here is what? It's just 2, right? Cost of 2, right? So the diameter of this graph is basically 2. Okay? It's basically 2. So there are few shortest path cost which is 2. 103, 123, 104, 204, 234, etc. Okay, or their reverse path since it's an undirected graph. Yeah. Okay, let's try something a little bit more challenging. Now it's not an unweighted graph. Now it's a weighted graph. Okay, undirected weighted graph. So what's the diameter of this graph? What's the diameter of this graph? Again, we do the same thing, right? Try to find the shortest path between every pair of vertices, right? Okay. So That's right. Between 0 and 1, what is the shortest path cost? Is it just the edge? It is, right? So the current greatest shortest path cost I found is 8, right? Okay, 0 to 1 is 8. 0 to 2? 4, right? Yeah. So is it bigger than 8? No. So current greatest shortest path is still 8. 0 to 3 is just 1, correct? 0 to 4 is just 2, right? 1 to 2? Is it 10? Can you get anything better than 10? No, right? So it's 10. So update the greatest shortest path. So this is 10. Okay? Next, 1 to 3. 1 to 3, is it 14? Is it? Yeah, it's 9. 1, 0, 3, yeah, it's 9. It's still not better than 10. It's not greater than 10. Okay, 1 to 4. 1 to 4, is it more than 10? 1 to 4. No, it's still 10. It's 1, 0, 4, right? It's still 10. Okay, it's not better than 10. Okay, 2 to 3. 4, correct? Yeah, 2 to 4. 2 to 4, is it? Yeah, 6, 2, 0, 4, okay? Not 2, 3, 4. 2, 3, 4 is 7, so it's 2, 0, 4 is 6. Okay, 3, 4 is just 3. So the biggest, shortest path you have now is 10, yeah? So basically it's this, 10, okay? Okay, so basically in order to find the diameter of a graph, you know you have to find the shortest path between every pair of vertices in your graph, right? So basically that's all pair shortest path, okay, rather than a single source shortest path, okay? From a single source to every other vertex, this is between every pair of vertices in your graph. Okay, so can we, okay, so the definition is very simple, okay? Just find shortest path between any pair of vertices in the given directed weighted graph. Okay, so can we use what we have learned so far to solve this problem? Can, right? Can, right? So if it's an unweighted graph, what can we use? Yeah, we use BFS, we can find, if you just pick one source, we can find from that source to every other vertex, right? Since we want every pair, we run BFS on every vertex as the source, correct? Yeah. So you just call BFS V number of times, okay, on each vertex. Okay, so this will be a V times V plus E algorithm, right? Which in the worst case is big O V cubed, when the number of edges is big O V squared, right? Yeah. Okay, on weighted graphs with positive edges, what can you use? Well, number one, you can use Bellman-Ford, definitely. Just call Bellman-Ford V times again, right? Once on each of the vertices. Okay, what's the time complexity? Again, V times VE. Okay, since E can be V squared, oh, this one is even longer time, big O V to the power 4. Okay, or you can just use Dijkstra. Dijkstra will be slightly faster. Call Dijkstra V times. Again, once on each vertex. So this one will be V times V plus E times log V. Okay, which is V cubed log V. Okay, if E is equal to V squared. Yeah. So can we do better? Of course we can do better. In the worst case, we can do better. Okay, so that's the point of this lecture. Okay, so the better part comes from this algorithm, okay, called Floyd-Warshaw's algorithm. Okay, so Floyd-Warsaw is basically a DP algorithm. Okay, but here I won't really discuss the actual DP formulation. After this slide, after I describe the algorithm, I'll just tell you the brief idea of how it works. Okay. So Floyd-Warsaw, okay, instead of your normal Bellman-Ford or your Dijkstra algorithm, which uses a D array, a distance array, right? Here it uses a distance matrix because you want to keep track of the shortest path between every pair of vertices. So it uses a 2D matrix, a 2D distance matrix. Okay, size V times V. Okay, so Dij will basically contain the shortest path cost between vertex I and vertex j, right? So initialization, how do you initialize this distance matrix? Okay, so for the diagonal, that is Dii, you set it to 0. Right, shortest path from a vertex to itself is just 0, right? And then for Dij, any ij, you set it to be the weight of the edge ij if there is an edge from I to j. Otherwise, you just set it to infinity at the start. Okay, so this is initialization. Okay, so after Floyd-Warshaw's stop, Okay, then every entry will contain the shortest path cost. Okay, every entry Dij will contain the shortest path cost from I to j. Okay, so what does Floyd-Warshall look like? Very simple. It's just four lines. That's why it's called four-line wonder. Okay, it's 3 for loops. Okay, 3 for loops, and then inside there one statement. Okay, so remember it's very simple to remember the sequence of the for loops. Okay, first you have the outer loop, which is a k variable that goes from 0 to v minus 1. Okay, then after that you have ij inside, the 2 nested loops. Okay, that loops through all the pairs of vertices ij. Okay, goes from 0 to v minus 1 also. Okay, then inside there you have this statement here, which goes like this: Dij is assigned the minimum of Dij and Dik plus Dkj. So what is this? What is this statement doing? Okay, you can imagine that this is basically a relaxation statement. Okay, you're performing relaxation. Okay, what it means is this. Okay, currently, if I have some shortest path estimate, right, for the shortest path between I and j. Okay, now I look at the shortest path from I to j using k as an intermediate vertex. Okay, so if I use k as an intermediate vertex and I can relax the path cost, okay, for Dij, then I update it. That's what it means. Okay, that's what it means. Okay, so if you see, the analysis for this is very simple. It's just 3 nested loops, right? Each one big O of v number of iterations. So it's big O of v cube. Okay, this is big O of v cube. Okay, and you'll see that this is just slightly faster than the worst case for Dijkstra's. If you run Dijkstra v number of times, right? Dijkstra will be v cube log v. Okay, so this will be better. Okay, in the worst case. But if you have a sparse graph, that is when E is not big O of v squared, but when E is big O of v. Realize that actually Floyd-Warshall will not be better than Dijkstra, right? Because Dijkstra is just what? V squared log v instead of v cubed log v. Okay, so then if you have a sparse graph, use Dijkstra, run Dijkstra v times. If you have a dense graph, okay, where E is equals to big O of v squared, use Floyd-Warshall. Okay, use Floyd-Warshall. Okay, so in the worst case, if all your graphs are dense graphs, then you, with all you have learned, right, you cannot get better than this one, big O of v cube. Okay, so if it's big O of v cube, then probably you can only run it on small graphs lah. Okay, nothing more than maybe 1,000 vertices. Yeah, because v cube is already 1 billion already, right? Yeah. Okay. So once you know this, you can apply this to your PS6. How? Okay, go for lab tomorrow. Okay, they give you some idea. Okay, so what's the basic idea? Okay, why 3 lines and then 1 relaxation statement? Okay, what's the basic idea? Okay, the basic idea is this. At the beginning, okay, at the beginning, okay, between any I and j, okay, I don't consider any other intermediate vertices, okay, to find the shortest path. So at the beginning, okay, so disregard this. I only consider the direct edge, okay, when I look at the shortest path, if there is a direct edge, okay, which is where the initialization comes from, right? Yeah, for any ij, okay, other than the main diagonal, which is all 0, if there's an edge, set the shortest path cost to be the weight of the edge. Otherwise, set it to be infinity. Okay, then I have a for loop, right? The triple nested for loop, right? So the outer loop will run through k from 0 to v minus 1. What it means is this. Okay, for the first iteration of k, for any ij, I just use vertex 0. Consider vertex 0 as an intermediate vertex. Does it improve the shortest path? If it does, update the cost. And then it will run to k1, right? So now I include 0 and 1. Does it improve it further? If it improves further, update. So you keep doing this until you have considered all possible vertices as the intermediate vertices along the path. Once I've done that, it's guaranteed that I must find the shortest path, right, from I to j. Okay, that's the main idea. Okay, that's the main idea. Of course, here you'll see that, I mean, based on what we have taught you, right, the number of the size, the dimension, okay, of your memo table, which is in this case your distance matrix, right, will be the number of parameters you need, right? So actually here I have 3 parameters. So I have k, I have I have j. How come my memo table is only 2 dimensions? Okay, that's the difficult part. Okay, so that's the part I want to explain. Okay, so how did Floyd Warshaw, that's the guy who invented this, come to this conclusion? I only need 2 dimensions. Okay, we'll leave it to some other further courses to explain this to you. Okay, yeah. Okay, so basically this is the recursive. This is the recurrence lah. Okay, this is the recurrence for it. Okay, but in this recurrence you will need 3. Basically, you need 3 dimensions. Okay, you need 3 parameters. Okay, so you can read this on your own. I won't talk about this. Okay, so what's the usefulness of all-path shortest path algorithm? This Floyd-Warshaw algorithm. Okay, one usefulness is that it's very useful for pre-processing purpose. Okay, so I believe that after you've done all your so many PSs, you now understand the usefulness or the utility of pre-processing all your solutions, right? Correct. Then you can answer your queries very fast. Okay. So if you have many queries you need answered, okay, pre-process all of them first at the beginning. Okay. So you might spend some time to pre-process it, but then afterwards all your queries is all one time, right? So for this one is once we pre-process the all-path shortest path information using Floyd-Warshaw, right? Then every query of what is the shortest path between I and j, I can answer in one time. Right? I just read it off the matrix. Yeah. Okay. So this is useful if you have lots of queries. Yeah, but if you have just like 1 or 2 queries, then it's not very useful lah. Okay. Okay. So any questions so far? Floyd-Warshaw? Very simple, like 3 lines of 4 loops and then 1 relaxation statement. Okay. Okay, so after we have looked at Floyd-Warshaw for solving all-path shortest path, okay, let's look at some other variants of Floyd-Warshaw. Okay, some other variants. So Floyd-Warshaw can also be used to solve many other problems by changing it a little bit. Okay, changing the relaxation statement a little bit. Okay, or changing the initialization a little bit. Okay, first variant. Storing and printing out the actual shortest path between any pair of vertex ij. Okay, so we have taught you how to use the predecessor array, right? In order to store the shortest path between the source and then any pair of vertices for single source shortest path, right? So in this case, we are computing all path shortest path. So it is not just a predecessor array. Now we have a predecessor matrix. Okay, predecessor matrix. Okay, so I have a predecessor matrix P again. Okay, so you let Pij be the predecessor of j on the shortest path from I to j. Okay, so it's like this. Okay, between I and j, okay, there's a path like this, right? I go all the way to j. Okay, just before j, which is its predecessor, right, is basically Pij. Okay, that's the predecessor of j along the path from I to j. Okay, that's what you store, Pij. Okay, so how do you update your predecessor matrix? Basically, it's like this. Okay, initialization. Okay, Pij is just assigned to j, is assigned to I. Okay, for any pairs I and j. Okay. Next, when you can relax, when you successfully relax, okay, perform the relaxation statement. Okay, what you do is this. It means this, right? If I can relax successfully, it means this. Okay, now I have this. I have a path from I to k, right? And then I have a path from k to j, right? This is the new path, correct? New shortest path, right? So what is now the predecessor of j along the path from I to j? It is basically the predecessor of j along the path from k to j, right? Correct? Yes? So basically, you just update it like this. Pij, which is predecessor of j along the path from I to j, is now the predecessor, is now Pkj, which is the predecessor of j along the path from k to j. Okay, so that's how you update it. Okay. Okay, so here's an example. Okay, so here's my D matrix, here's my P matrix, assuming that we have a graph like this. Okay, so I'll skip the process of showing you filling up the matrix. Okay, but after you run your flight washer, right? So this is what you get for your D matrix. This is what you get for your P matrix. Okay, so you can see that for 4, row 4, which is vertex 4, right? The shortest path from 4 to everyone else is infinity, except for 4 itself, right? Because you can see clearly that there's no path from 4 to anybody. Okay. So let's look at your predecessor matrix now. Let's say I want the shortest path from 3 to 4. So how do I get it from my predecessor matrix? So it's like this. Just go to row 3. Yeah. I look at row 3, right, basically it's like a predecessor array, right? A predecessor array, right, for vertex 3, right? Then how do I get the path from 4 to 3? Basically, you do your standard backtracing, right? So just go to column 4. I see it's 2. So I go to column 2, oh, I see it's 0. So go to column 0, oh, I see it's 3. Okay, so the path will be this, 4, 2, 0, 3. The reverse path. Then you just reverse it. You get 3, 0, 2, 4. Yeah? Get? Okay, so this is how you actually get the shortest path between any pair of vertex ij, okay, from your predecessor matrix. Okay, next variant, okay, the second variant of Floyd-Warshall, finding the transitive closure of a graph. Okay, actually, Floyd-Warshall developed his algorithm to solve this problem, okay, and not the all-pair shortest path problem. Okay, but he was made famous for the all-pair shortest path problem instead of this problem. Okay, but it was actually intended to solve this problem, okay, called transitive closure. What's transitive closure problem? It's basically this. Okay, given a graph, determine if vertex I is connected to vertex j. So given any pair of vertices, check whether I and j, okay, they are connected via either an edge or indirectly via a path. Okay. So in other words, you want to check whether j is reachable from I. Given any pair of vertex ij, check whether j is reachable from I. Okay. So how do I modify Floyd-Warshall now to solve this problem? Okay, very simple. Modify D, the D matrix, so that it only contains 0 and 1. Okay, only 0 and 1. So 0 means that I is not reachable, or j is not reachable from I. So that's what it means. 1 means that j is reachable from I. Okay? So initially, you just set dii to be 0. Right? Why is it 0? Why is dii 0? But at the beginning, you don't know whether there's a cycle that comes back to I itself, right? Correct. So at the beginning, there's no edge, or there's no path, right? From I to itself. So you just set it to be 0 at the beginning. Okay, next, for any ij, okay, dij is set to 1 if the edge exists. Okay, so if the edge exists, it means that j is reachable from I. Okay, so set it to 1. Okay, 0 otherwise. Okay. And then you still have your 3 nested loops as per normal, but now you change your relaxation statement. Okay, to be like this. Okay, dij is assigned dij bitwise or dik bitwise and dkj. Okay, so what does it mean? It means this. Okay, if dij is already 1, okay, dij bitwise or if anything is still 1, right? If j is already reachable from I, and it's always reachable from I. Okay. Next, if dij is not reachable from I currently, okay, then I look at some intermediate vertex k. See whether I can use that to bridge I and j, right? So basically like this, right? So I have I. Okay, then I have k. Then I have j. Okay, if k is reachable from I, that means that there must be a path like that. If j is reachable from k, there must be a path like that, right? Okay, so it also means that dik must be 1, dkj must be 1, right? So if both is 1, then bitwise n of 1 and 1 gives you 1. Meaning there is a path, there is a way to bridge I and j using k, okay, as some intermediate vertex. Okay, So if either you don't have this or you don't have this, then either this is 0 or this is 0. Okay, the n will give you 0, right? So that means that I cannot use k to bridge I and j. Okay. Okay, so why do we use a bitwise operation, bitwise n and all instead of logical n and all? Okay, because here we are working with integers. Okay, in Java you cannot use logical operators with integer values, right? So you use bitwise operator. Okay, and it gives you the same effect as the logical operators when you work with 0 and 1s. Okay, so here I say it's faster. Actually, currently with compiler optimization technologies, maybe it's now no longer that much faster, okay, than using Boolean operators. Okay, but you can try it out lah. Sometimes it might be faster. Okay, depending on your application. Okay. Okay, so this is the second variant, which is the transitive closure. Okay, yet again, let's look at an example for transitive closure. Same thing. Okay, I have the same graph. Okay, I have the same graph. So at the beginning, your D matrix is initialized like this, right? The main diagonal will be 0. So whenever there's an edge between any entry here, it's set to 1. Otherwise, it's set to 0. Okay. Then at the end, after you run Floyd-Warshall variant 2, okay, on this graph, here's what you get. Everything will be 1 except the last row, which is 0, right? If you just eyeball the graph, you can see that it's 0. I mean, 0 can reach 1, can reach 3, can reach 2, can reach 4, right? Same thing. 1 can reach 0, can reach 1, can reach 2, can reach 3, can reach 4, and so on and so forth, except for vertex 4. Because vertex 4 has no outgoing edges. So nobody is reachable from 4. Yeah. Okay. So this is the second variant, solving the transitive closure problem. Okay. Third variant. Okay. Solving the minimax problem or the maximum problem. Okay, so what's the minimax problem? The minimax problem is basically this. It's the problem of finding the minimum of maximum edge weights along all possible paths. Okay, from vertex I to vertex j. Okay, so maximum is basically the reverse lah. Finding the maximum of minimum edge weights along the path of all possible paths from I to j. Okay, so what it means is this. Okay, minimax is this. Okay. For any ij, okay, for a single path from I to j, okay, I pick the maximum edge. Okay, I pick the maximum edge. Let's say this edge is E. Okay, then for all possible paths, okay, there could be many possible paths like between I and j, right? I pick all the maximum edges, maybe E, E prime, E double prime, etc. Right? Then among all these, I simply find the minimum. Okay, I simplify the minimum. So it's the minimum of maximum edges along all paths. Okay, this is the minimax problem. Okay, so here your distance matrix Dij will store the weight of this minimum maximum edge weight. Okay, okay. So where have you seen this problem before? Where have you seen this problem before? Have you all seen this problem before? You definitely have seen this problem before, right? PS4, right? Correct? Find a path where the maximum edge along the path from I to j is minimized, correct? Yeah. So you have actually seen this problem before. It's PS4. Okay, it's PS4. So you already have one way to solve this, right? You already have one way, which is what? Build the MST. Yeah, exactly. So MST is one way of solving the minimax problem on a graph. Okay, so here's another way of solving it using Floyd-Warshall. Okay. So again, okay, here's the modification of Floyd-Warshall. Okay, so initialization, the main diagonal set to 0. Okay, then dij will be the weight of the edge ij if it exists. Okay, if not, it's infinity. Okay. So your three-nested loop will be as per normal, and then I just change that relaxation statement. Okay, to become like this. Okay, dij will be the minimum of dij and the maximum of dik dkj. Okay, so what does this mean? Okay, what does this mean? Okay, it just means this lah. Okay, if I look at some intermediate vertex k, okay, for I and j, okay, so I have j here, I have I here, right? Then I look at k. So if there's a path from I to k and a path from k to j, right? Then this must be a one path, right, from I to j using k as an intermediate vertex, right? So here there must be a maximum edge. I want to find the maximum edge along this path, right? So what I do? I get the maximum edge from I to k, right? Which is this one, dik. And then I get the maximum edge of the path from k to j, which is this one, dkj, right? Then the maximum among these two must be the maximum edge along this path, right? From I to j, which is why you use this. Okay? So this is the maximum edge along path from I to j using k as intermediate vertex. Then I compare it with the current minimum max edge weight that is stored for ij. Okay, so you look at it at dij, right? Then you check which one is smaller, right? Is it this one or is it this one which I found? Which one is smaller? Just pick the smaller one to update dij. Why you want the smaller one? Because I want the minimum of the maximum edge weights, right? So that's why you find minimum between these two. Okay? Okay, so let's look at example again. So same graph. Okay, you have the same graph. Okay, let's look at the minimax path from 1 to 4. From 1 to 4. Okay, before that, let's look at the D, okay, at initialization phase. So you see, same thing, main diagonal is 0. Okay, if there is an edge between any cell, okay, between the row and column of any cell, just set it to the edge weight. Otherwise, set it to infinity. Okay. And after you run flight wash off, okay, this is what you get. Okay, this is the D final. Okay. So let's look at the minimax path from 1 to 4. Okay, from 1 to 4. Okay. So what's the minimax path? You just eyeball this, right? Just eyeball this. You see that it's this 1 to 3 to 0 to 2 to 4. Okay. With 4 being the maximum edge along this path. So can you find? So is this is for the smallest maximum edge along any path? Is this the smallest? Is this the smallest? Yes. So, question: is 4 the smallest maximum edge weight along any path from 1 to 4? It must be, right? Why? Because there's only one outgoing edge from 1, right? Which is this edge, 1, 3. So in order for 1 to reach 4 through any path, it must use 1, 3, correct? It must use 1, 3. Okay, and of course I have found this path, right? Where every other edge, okay, 3, 0, 1, 2, and 2, 4 are only weight 1. Okay, so 4 is the smallest maximum edge. Okay. Okay, so this is the third variant, solving the minimax or the maximin problem. Okay, last variant, detecting positive and negative cycles in a graph. Okay, you can use flight washer to detect positive or negative cycles. Okay, so how do you do this? Okay, for this one, it's basically just using your standard APSP. Okay, using your standard APSP for flight wash-off. Okay, but the only difference is this: set the main diagonal to infinity instead of set it to 0. Okay, so everything else is exactly the same initialization. okay, as for APSP. Okay, after that you run Floyd-Warsaw. Okay, after that you just recheck the main diagonal. Okay, if the value is smaller than infinity but bigger or equal to 0, that means that there must be a positive cycle, right? So the weight of the shortest path from 0 back to itself, if it's positive, that means there is a positive cycle, right? So on and so forth, right? But if the weight is smaller than 0, that means that there must be a negative cycle. Okay, a negative cycle exists. Okay, so you can use Floyd-Warsaw not just to detect negative cycles but also positive cycles. Okay, both positive negative cycles. Okay, so in this case, the same graph here, you don't have any negative edge weights, so all of this is positive, right? The main diagonal all positive. Okay, except for 4, which is still infinity. Yeah. Okay, so I have quickly shown you 4 variants of Floyd-Warsaw algorithm. Okay, there is a Floyd-Warsaw demo code that is given to you together with the lecture notes, right? So it's quite simple code, I won't go through it, but it lists down all the 4 different variants you have, so you can take a look at it, okay, run it, test it, play with it, okay? Okay, so very quickly, it's a very short lecture, okay, summary of this lecture. Okay, we give you the introduction to APSP problem, okay, using one motivating example, finding the diameter of a graph. Okay, then we introduce Floyd-Warsaw DP algorithm to solve this. Okay, yet again, I want to say Floyd-Warsaw is a DP algorithm. Okay, it is not just another graph algorithm. Okay, it is a DP solution. Okay, and after that, we introduce 4 variants of Floyd-Warsaw. Okay, to solve 4 different kinds of problems. Okay, so that's the end of the lecture. Okay, very short lecture. Okay, we take 6 minutes break. You come back at 10:45 and then we will start your quiz 2. Okay. 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 I am still waiting for my TAs who's going to help me distribute the papers and invigilate. Okay, so we'll wait for a while. I think we have enough time. Okay, we have enough time. Don't worry, the quiz is not very long. It's a short quiz. Okay. Okay, the TA, hello. Yeah, the TA will start passing out the script now. Okay. Okay, as he is passing out the script, I want you to do something. Okay. Okay, go to IVLE. Go to IVLE. Go to IVLE. Okay, log into IVLE. Okay, log into IVLE. Okay, go to Gradebook. Go to Gradebook. Go to gradebook. Okay, go to gradebook, Okay, look at this. Attendance for written quiz 2. Okay, there is an item called attendance for written quiz. Go verify it. That is marking your attendance. So that was the whole point of asking you to bring your something that can connect to internet. Yeah, okay. Okay, please don't start yet. Make sure everybody has the script first. But you can write down your metric number first. Okay, write down metric number, write down your tutorial group. As usual, if you cannot remember your tutorial group number, write down the time. Okay, write down the time. And also write down your tutor's name. Yes. Write down your tutor's name. Okay, so don't start yet. Don't start yet. You will have enough time. Okay, who hasn't gotten the script? Okay, then. Okay. Okay, please don't look at your script first. Put it down. Put down your scripts. Okay, who Who still doesn't have the script? Who still? Raise your hand if you don't have the script. Okay, anyone doesn't have the script, raise your hand. Anyone? Okay, if everybody has a script, you can start now. You got 45 minutes. We'll end at 11:43, 11:42. Okay, just your attention. Okay, for question 5B, okay, some of you ask me, do I still need to find the shortest time? No need. Okay, no need, no need. Just follow what is said here, described in question 5B. That's all you need. Okay, you don't need to find the shortest time anymore. Okay. You have 5 more minutes. Okay, another announcement. Okay, that was not on purpose. Okay, so quite a few students ask, are the time for the doors to open all the same? Obviously not. Okay, obviously not. Okay, I give you 5 more minutes if you need to change your answer after that revelation. Okay, 11:50. Okay, you suddenly need to change answer with that revelation. Okay. writing, pens down, stop writing. Okay, here's what we're going to do. Okay, so there are 3 blocks here, okay, in lecture theatre. Okay, for the leftmost block, on my left, okay, every row pass to the last student on your left. Okay, middle block also, every row pass to the last student on your left. For the last block on my right, pass to the last student on your right. Okay? And then just sit tight while we collect and count the papers. Please don't go off yet, because we're going to count the papers. Make sure none is missing. Don't go off yet. Sit tight, sit tight. Okay, for those who didn't mark attendance, okay, just now I asked you all to mark attendance. How? Okay, how do you mark attendance? Go to gradebook. There is this new item here. Okay, attendance for written quiz 2. Just verify that. Verify it. That's marking attendance. If you have not done it, please do it now. I want an accurate count. Okay? Please be a little quiet because we're counting. If they can't count properly, then you all have to keep waiting. Okay. Okay, just to announce that for next week there's no content anymore, so we will just go through the past year exam papers. Okay, revision. Okay, revision for next week.